Okay, good morning, everyone. Okay, we come to lecture 5. Okay, lecture 5. So we'll continue on the topic of non-relativistic limits. Relativistic limits of Dirac equation. Equation. Okay, so we briefly review what we learned last time. So last time we learned the Dirac equation. That is IH bar derivative on time on this big wave function equal to the Dirac Hamiltonian. The Dirac Hamiltonian. The Dirac Hamiltonian has a form of this dot P. This is P minus E over CA, and then C, and then plus beta MC square plus this electrostatic potential, and then this wave function. Okay, so this is the Dirac equation under electromagnetic field, and then we let this big wave function. It is a 4-component wave function. Then there are 2 parts: the exciton part, and then the positron part. So each of this is a 2-component spinor wave function, including the spin up and spin down components. And then we're going to take the relativistic limit. We put this inside, and then you quickly get 2 equations, 2 set of equations. Okay, so we're just reviewing what we have done last time. So these 2 equations. Okay, so this is equation 1, equation 2. Okay, so equation 2 can be written as this one can be written as this chi equal to 1 to MC Okay, so okay, can be rewritten as this. After one iteration. One iteration. So you can go back to check the last lecture. So that is the relationship between. So here you need to pay attention to the order. This is 1 over C. This is 1 over C here, 1 over C square here. Okay, so we are using the speed of light, this 1 over C factor to do the expansion. You see it's a big number, okay? So in the non-relativistic limit, so you just only need to keep one or two orders of these terms. So then you put, this is equation 3. Put equation 3 into equation 1. Okay, we get this IH. Okay, so square plus MC minus 1 4 I need to make it smaller. Okay. Okay, so this is term 1. So we dealt with it last time. And this is term 2, which we're going to deal with in today's lecture. So in term 1, let me just quickly review term 1. In term 1, this is because okay, so this equal to, last time we already get the result, 2MC sigma dot B. Okay, so this is the Zeeman effect. The Zeeman effect, or the Zeeman term. Okay. So in last lecture we used this identity, which we're going to use it again. So let me also briefly talk about this. Anyway, in this whole derivation here, I'm going to use this so-called Einstein convention. That means when two indices appear, then that automatically means a summation. Okay, so this one, I J, so this is equal to 1 when I equal to J. And then there's a second term that last time I also talk about, sigma I J. So here, this thing I need to this equal to this IJK. So sum over K. So last time I didn't talk about sum of K. I thought it's just K. But actually in my notes, I actually use this Einstein convention that when there are 2K appear, that means you need to sum over K. So automatically this will give us the this summation here is automatically included, and that is how you have the A cross B K, and then the whole thing just become A dot B plus dot A cross B. So the dot product is because the summation of K is included. Okay, this is I. This is I. Okay, I hope it is clear. I hope it is clear. Let me slightly adjust it. Yeah. Okay. Okay. Yeah. Okay, so this result, we're going to use it again in today's lecture. Okay, so and it's good to have it here, and just and also make the clarification or correction that this k implies the summation over k. So that is this. I actually I was a little bit puzzled why I kind of did not say the summation last time because when these two are different, so only the z term will be present. So there's only one term, but you can also sum over all the terms because when they overlap with the x or y, then it's automatically 0. So you can actually sum over them. Okay. So here, whether you sum over or not is the same result. But when you sum over them, then this will that sum over is important to give you this dot product, the dot product. Okay, so now let's go to second term. Okay, so that is the main content of today's lecture. This second term is okay. This is second term. Okay, so let's go to term 2. So this second term, let me see. So we're going to reverse this order here. It's good to deal with both of these together, but now they're separated by this term here. So we are going to use this formula. If you have two operators like this, so you're going to have AB here. You're going to minus BA here, and then plus the BA. Then you have BA AB commutator. So this simple formula. So you can use this simple formula to switch the order of the operators. Okay. So this is AB, now this is BA, and then you compute the commutator. So we're going to do it here. So let me use this copy and paste function. Okay, this can accelerate a little bit. No, let me see this. Let's only deal with this term here. Only this term. Okay, let's deal with this term. So this term equal to you switch the order. You switch the order. Switch the order. And then plus the commutator. Copy. The order is important. Okay. Okay. And then you have the commutator. Okay. Okay, let's calculate the commutator. Let's calculate this commutator. This commutator equal to okay, you can neglect this term because MC squared is a constant. It commutes with everything. Okay, so you can already delete this, delete the MC square. Okay, so you take away this one. Okay, so you only have this. Then okay. Then you also don't need to worry about the sigma, because sigma commute with all the terms here. Okay, commute with all the terms here. So you only need to worry about the pi. Then you can have the dot product outside. Okay, you can have the dot product outside. It doesn't matter. Okay. Then let me see. Then let's focus on this part. Yeah. T minus this. Then you're going to write it out as this minus ECA. ECA. Okay, commutator. Then you're going to have 4 terms. You're going to have 4 terms. Let me write it here. You're going to have 4 terms. You have IH bar T. 1 term. 2 terms. And then 1 more terms. And then I need some space. And then ECA. Okay, you're having 4 terms here. You're having 4 terms here. So let's deal with them one by one. So this term is 0. Because derivative on time and derivative on space, they commute. Okay. And then these two are they're just functions. Okay, there's no derivative, so they also commute. So you only need to consider this term, these 2 terms. So what is this? So whenever you deal with a commutator between a derivative and a function, the result is just the derivative on the function. You can actually prove this easily. Okay, so the result is just you do the derivative on the function and multiply it. Okay, the same here. The same here. The same here. So you just do the derivative on the function. Okay, on the function. Okay, so eventually, you get what? You get let me see. You get IE H bar, and then negative this minus this. Okay, eventually you get this. So can someone tell me what this is? Are you paying attention? Can someone tell me what this is? Just one letter. Give me one letter. What is that? A, B, C, D, E, F, G, one of them. Okay. Okay. Did you forget your magnetism? Okay, this is E. Okay. This is E. Okay, this is just the electric field. Okay, so yeah, help you to review the electromagnetism. Okay, so this is just the expression for E. Okay, it's very simple. So our result It's very elegant. Just E, okay. Okay, so this whole term eventually become just IH bar E dot sigma. Okay, so term 2. Okay, copy. So term 2 becomes negative 1/4 MC. And then you reverse it, right? You reverse it. So you have twice of this. Okay, you reverse it. Okay, that's one thing. And then copy this, you reverse it. Copy. Okay. And then plus a commutator. So this commutator is what? Is IEH bar E. So this E needs to dot the sigma. So it's E dot sigma. Okay, E dot sigma. And then let me. So these are okay. This is one term. We can just simply write a square here. So just to simplify it. Okay. And then in the second term, you also have this pi dot sigma. And then here you have the E. Okay, so the second term becomes something like that. Of course, you multiply the wave function. So this is the second term. And there's a plus sign here. Okay, is it okay? Okay, so now let's deal with them. Furthermore, this one, pi dot sigma square. Okay, so this one, we already got it last time. So I dealt with it last time. That is basically this term 1 here. Basically term 1, but without this 1/2 pi. So it will be this thing. It will be this. This thing will be what we need. Okay, so but without the 2m. Okay, so this is this thing. Okay, this is this thing. Okay, you need to know that we want to expand it up to the order of 1/c squared. So every time you see the 1/c here, you can neglect, because here we already have a 1/c squared. Okay, so here let's go back to this. This is the equation. Now this term 1 give us a 1/c term, which is the Zeeman term, 1/c. Okay, so this term has 1/c squared. So basically, anything that you expand here, as long as it contains the 1/c factor, you can neglect. Okay, so that we only want to keep all the 1/c order. Okay, we only want to keep 1/c squared and 1/c order. Okay, so here you can just equal to pi square. Let me just expand it even more. Pi is p plus minus E/CA minus EHC. So equal to just p square. Only keep the 1/c order. Keep 2. in term 2. We only keep 1 to 1 over c. So there's a 1 over c here, there's a 1 over c here, and you can neglect. Okay. So this is p square. Okay, then and since it's a vector, so you can basically just take the magnitude. Okay, you can basically just take the magnitude. You can take the magnitude. Okay, and then the second term, this term. This term is, what is this? Okay, so this one, let me see. This one is total energy. This is total energy because IH bar T equal to this, right? So you have the Hamiltonian, right? So what IH bar over T will give you total energy, because that corresponds to the Hamiltonian. So this is rest mass. This total energy include the rest mass energy, and this is potential energy. So what is left is just the kinetic energy. So just the kinetic energy. Lowest order. Of course, you have the higher order term, but they will contain the 1 over c thing. So you only need to keep the lowest order. Okay. So that means this whole thing will just give you p square times p square. Okay, we only give you p square times p square. So this whole thing, copy, will just give you p to the power 4 2m. Okay, so this first term is very simple, just p to the power 4 over 2m. Okay, so we dealt with this one. Let me just group it here. P to the power 4 2m. Okay, something like that. Okay, so then let's deal with this term, this thing. Okay, this is the thing that we need to deal with. Copy. Okay, so then we are going to reuse the formula. So we have this formula here. This formula. This is the formula that we use, right? Copy. So this is the formula we derive. So you just erase all of this. Don't need this. Don't need this. Okay, so this is the formula that we derive. So we're going to use this formula. Use this formula, then this one, this is A, this is B. So you're going to have pi dot E plus I sigma. Then this will be pi cross E. This will be pi cross E. Okay, so let's deal with pi cross E. This thing. So this equal to IJK J K. So this is the curl. So you need to sum over J and K. The Einstein convention is there. And then here you have, we apply the same technique, reverse the order, and then take the commutator. Okay. So what is this commutator? So this commutator equal to pi j, this is j, right? Plus ECAJ EK. Okay. Then this will be PJ EK. This will be this is negative. This is negative. Okay. So negative EC over AJ EK. So this term is 0. Why? Because A is a function, E is also a function. They're not derivative, so they come in. But this one is not, because P is a derivative and E is a function. So this is IH is H bar over I derivative EK. This derivative will be only on the J component. Will be only on the J component. And when you are taking a commutator between a derivative and a function, the commutator is just a derivative on the function. Okay, you can check this by yourself. So this is just a derivative on the function. Okay, so eventually, so what is this? So this is just the cross product. The cross product of E and pi, and then the I component. Okay. Let me see. No, this one is this. Group it together. Group it together. Okay. Yeah, it is this term. Okay. So you have this whole thing. This whole thing equal to IJK EK, this, and then plus IJK let me see, H bar, and then DJEK. Okay, so this one is E cross pi, E cross pi, I component. And this one is curl over E, also the I component. Let me see. This is actually negative. There's a negative here. Because this is K. Let me see. Yeah. Negative, because you need to reverse the K and J, because this is K, this is J. So here is a negative. Okay, this is negative. Okay. Or you can let me just add one more line then, make it clear. Copy. So you change this. into K and J and add the negative sign. Okay, so I hope it's clear. Moving slowly, but I hope it is clear and you all understand. Okay, so we're going to, let me see, summarize it. Okay, this thing, copy. It's going to equal to, okay, you have this term and this term. So you just put it together. You have a dot product here. Okay, you have a dot product here. Okay, so you're going to have pi dot E minus I dot E cross pi and plus H bar sigma dot this. So this I and this I cancel. Okay, so you have a term like this. You have a term like this. So we're going to take this, go to, this is P to only P. Why? Because there's a 1 over C here. Okay, so this term will just go to the next order. So we only take the leading order here. Because all the 1 over C term here eventually will give you 1 over C to the power 3. Okay. So then you copy this, and then you just change all the pi. Change all the pi to P. And then this will take P. Yeah. Okay. So let me see. And this thing will be let me see. Will be 1 over C derivative on B. Okay, and also neglect. Neglect. Okay, because you this next order term neglect 1 over C term. Okay, so you only have 2. You only have 2 here. So eventually, so what is term 2? Let me see. Okay, this is the term 2. You have this, we got it, P to the power 4 to M. And then we have this thing that we got. This thing we got is this thing. Okay, is this thing. So eventually, term 2 becomes and then P to the power 4 to M plus I EH bar P dot E plus EH bar E cross B dot sigma. The sigma can be dot on either side is because sigma commute with E and P. Okay, so it's okay that okay, so term 2 becomes this. Then we can write it term by term maybe. So the first term you combine this A, C, P dot E, and then this. Okay, so now let's combine term 1 and term 2. So you're going to get a new Dirac equation. That is this. You just put all of them together. A plus MC and then you have this term. It doesn't matter which way dot. Okay. And then the Zeeman term. And then minus this term. Okay. So, and then multiply the wave function. Okay. So this is, I call it equation 4. Okay. So there's one problem in this equation. Do you notice there's one problem in this equation? It's not done yet. There's one problem in this equation. Do you notice? Which term has some problem here? Okay, there's a requirement for Hamiltonian. This is derivative, so that means this is the effective Hamiltonian of the Dirac equation in the non-relativistic limit. Okay, this is an effective Hamiltonian. Not effective, is a non-relativistic limit of the Hamiltonian. There's one term here that is problematic, because there's one requirement in Hamiltonian, that is the Hamiltonian must be Hermitian. Okay, when it is Hermitian, it will give a real energy eigenvalue. So this is a requirement. So which term here is not Hermitian? Can someone tell me? There's one term here is not Hermitian. Which term? This term? Which one? Just tell me which one. Which term is not Hermitian? Hermitian means you take the complex conjugate and do the transpose, you get the same thing. So this term is not Hermitian. So this term is non-Hermitian. So that means we still need to do some correction. We're not done yet. Okay. So what is the problem here? What is the problem here? The problem here is that this wave function here is not normalized. It's not normalized because when you solve it, you need to the wave function need to be normalized, and you need to know this is not the complete wave function. The complete wave function include the positron part. Okay, so the positron part here is small, but it's non-negligible. You're expanding that small part, but after the expansion, you need to go back and take care of the normalization condition. So when you have a normalization condition of a 4-component wave function, you need to deal with both components. So this one plus this one need to equal to 1. Need to equal to 1. So if you only have this part equal to 1, that is not normalized. You still need to have this part. Okay. So in a leading order term, in a leading order, so let's go back to chi. Let me see, where's chi? Oh, it's at the very beginning. Okay, chi equal to this thing. So in a leading order, it is this term, 1 over c. And you can change this pi into p to the leading order. So you can copy this. Then you can change this just into p. Just into p. Okay. So you don't need to worry about the sigma there. Okay, because that will not change this product. Okay. Approximately. Okay. So the normalization condition will become. By the way, this p is still an operator. Okay, it's still an operator. So this will be p square. Then you have 4m square c square. They just sum them together. Then we want to get the normalized wave function. You can do it this way. You can have 1 over p square. Then you divide it by 2. And then multiply also this. You can do it this way. You can check. This one multiply this one will give you this. If you neglect the 1 over c to the power 4 term. Okay, to the power 4 term. Okay, to the order. Is okay? These two multiplied together will give you this. If you neglect the 1 over c to the power 4 term. Okay, then you can rename this as a normalized wave function. And this one as a normalized wave function. Okay, to the order of 1 over c square here. We neglect the 1 over c to the power 4 term. Okay, so now that means you need to apply this on the right hand side of equation 4. So this is equation 4. Okay, so when you apply to it, let me see. So let's do it term by term. You consider the first term here. You consider the first term. Then you just apply this. You apply this on this. Then you can easily know that they commute. They commute. Okay, you can easily tell that they commute. So you can put this thing to the other side. Then you have the 1h bar dt normalized. Okay. So you do the same thing here. You put it on this term. You put it on this term, on this term, on this term. Okay. So what you want to do is you want to put this 1 over p term here. Like you have a 1 over 1 plus p. Yeah. Okay, you have this term. Okay. You apply on here, and you want to move it all the way to here to make this function normalized. So you're hoping that it will commute with every term, just like in the 1 over, in this term it commute, right? So it's very easy. You apply on this way, it commute, then you just move on to apply on the function, then the function become normalized. And you want to do it on every term, hopefully that they commute, and then you just move all the way to reach the wave function, so that the wave function will become normalized. Because you want to have a Dirac equation for normalized wave function, and this wave function is not normalized. I mean, this equation is correct, but the wave function is not normalized. Okay, so the Hamiltonian should be applied on the normalized wave function. Okay. So this term commute with every term inside to the order of 1 over c squared, except for one term. Which term? Which term? Which term? It does not commute to the 1 over c square order. There's only one term that you need to take care. All the other term you just switch the order directly. Okay. Which one? No, not the last one. No. Which term? Just give me one. 1, 2, 3, 4, 5, 6, 7. Give me a number. 1, 2, 3, 4, 5, 6, 7. Which term we need to take care of in the commutator? Yeah, you have 6 people here. Each one pick a number. If they're all wrong, then I'll pick the last one. Okay. Okay, lady first. You pick a number. Okay, Fahima. Okay. You think, oh, Zhao Yan pick this one. Okay. Okay, Ao. 6. 6. Okay, Ao. 4. Okay, this is Robert. Okay, Matt. Matt, you all take different one. Okay. Okay. Okay, Sun Yan. Okay. Okay, the correct answer is number 4. Okay, the correct answer. Okay. Okay, very good. Our Robert picked the correct one. Okay. All the others are incorrect. Okay. Okay, let's do it one by one. Okay, let me correct. Okay, so that means we did. Okay, let's do this. Copy. Okay. So let's just do one, you know why. Let's do one, you know why. Okay. Okay, let's pick the first term. Okay, copy. Okay, when you apply this on it, so you are going to switch the order, right? You're going to switch the order. And then take a commutator, right? And then take a commutator. And then take the commutator. Okay, so this commutator, if it is 0, then you know it they commute. Okay, so let's take this part. Okay, so you can delete the 1 because 1 commute with everything, right? Okay, so basically you only need to deal with the p square p square. I think you can take all the derivative outside and then times 2m, and then all you need to do is to take care of this one. Okay, square term. Okay, so the p term you can neglect because p commute with p. Okay, so eventually you need to take care of this part. Square. Okay, then you have a 1 over c here, so you can neglect it. Okay, so because you have a 1 over c, so you can neglect the 1 over c thing. Okay, so basically from the very beginning you can already neglect it. You can already make this p square. Do you get it? Because this is 1 over c squared, so when you have some extra 1 over c here, you can neglect it. Is it okay? So this commutator will be 0 to the lowest order. Okay, so you can neglect it because we only want to keep the 1 over c squared term. Okay. So anything extra thing here will give you a I mean, anyway, when you open it, there's probably some order that you need to take care of, but this one will be 0 to the lowest order. Okay, similarly, okay, let's go back. Then you can already very quickly. This term, you have a 1 over c squared here, right? Of course, this term commute because it's p4. Okay, always commute. And this one is a number, right? Always commute. Okay. This one, you have a 1 over c squared, and this is 1 over c squared. When you take the commutator, they multiply together, right? So you have a 1 over c, you have a 1 over c to the power 4. So that can also be neglected. Okay. And the same for here, you have a 1 over c, you have 1 over c. When you come and take the commutator, they multiply together, you have a higher order term. Neglect. The only term that will give you non-negligible result is this term, because this has no 1 over c. And this is a function, and p is a derivative. So they don't commute. Okay, so the answer is number 4. Do you get it? Do you get it? Okay, so okay, so commute all the terms on the left side to the order of 1 over 2, except this. So Robert, did you pick this one because you know it, or you just randomly?
But I figured it out when
Okay, you just randomly pick it. Okay. Okay.
I think I know why.
Okay, so in this one, commute with all the terms inside, except this one. This one will give you a non-negligible commutator to the power 1 over c squared, because you have a 1 over c squared here, and all the terms with the extra 1 over c will not. Okay, so we only need to deal with. Now you understand, right? Is that okay? Okay, now let's deal with this. Let me see. So this one will apply on this function. This is the electrostatic potential. Okay, so let's see how they commute with each other. So you switch the order. You switch the order, then you take a commutator, a plus. Okay, so this one, certainly the one commute with everything. So you have the p square commutator. And then the p square is just h bar this. So when you square, then you have a negative h bar here, h bar square here. Then you have this. Okay, so let's deal with this thing. So let's deal with this. What is this? So let's say you apply on the wave function. Okay, like this. Then you can do the derivative. Let me see. So basically, this means this minus this. Okay, you open the parenthesis, and then this one apply on here, and this one apply on here. So for this first term, you do the derivative first. You do one derivative. You have this one. You just use the product rule. Use the product rule. Okay. And then you still write this term. You still write this term. And then you apply the product rule one more time. One more time on the first term. And then, okay, so you apply the product rule on the first term. And then apply the product rule on the second term. Okay. Then the last term you write it again. So let me see. Let me see. This two term will cancel. Okay, this two term will cancel. And then these two term are the same. So you just have 2. Okay, you have 2. And then plus this. Okay, plus this. So this one, you can write it in this way. You can write it in this minus 2. I mean, you can check. Okay, you can check. Because you okay, you can write this in this way. Okay, in this way. Okay, so let me see. So if you write in this way, then sorry, I missed one thing. That's why I don't feel this right. Okay, you to this. Okay, 2. You can easily check it. You can easily check it. For example, let me quickly check it for you. You apply the product rule, square. And then plus minus. Yeah, no. And then minus this. And then this 2 will cancel. And then you have this. Okay, then you go back to this. Is that okay? Huh? So this one equal to this. Huh? You just do it reversely. Huh? You do the product rule here, open it, and cancel and cancel this one. Then you go back to this term. Okay. Okay, so that means eventually, this one will become this one will become 2. This term and this term partially cancel. So you have a okay. So you pull the wave function out because this phi is the wave function. This is the wave function. You pull it out, then you have 2 minus this, and then you have the wave function. Okay. So basically, it shows you that this commutator, copy, equal to this thing, copy. Equal to this. It show you this commutator. So then let's go back to here. Okay, you get this one. Copy. And then you just put this thing here. Copy. Just put it here. I think I need some space here. Let me pull it up. Okay, so let's deal with it. So what is this? This is just this is just E. This is just E, right? Let me see. Is it E? Yeah, this is just E, right? E equal to derivative on potential, right? So I think it's we have this formula here. This one. Copy. There's a negative, sorry. Okay, so we get this one. I mean, the full expression is this, but since we're going to neglect the 1/c term, so this is to the lowest order. Okay, so this will be negative E. So this whole thing will become, you cancel the negative, then this will become you add the I H bar here. Then the two already cancel. So you already have the 4 here. Then this you have the H bar over I. I mean this negative cancel. The H bar square, you multiply I and divide by I. Then by the way, this means here means sorry, here this is a dot. Okay, this is a dot. Yeah. When you have a dot product here, you equal to this. It's a yeah, because this is a vector, right? A vector multiply this. It's still a vector, a dot product. Okay, so so you have this dot E, and then plus H bar square A M C square. This is just dot P. This is just P dot E. Okay. So this term cancels this term. Where is it? Here. Okay. Cancels this term. Okay. Cancels the equation 4, the non-Hermitian, the non-Hermitian term here. Cancels the non-Hermitian term. Need some space. Okay, so this is this, the Hermitian term. Yeah. Okay, in equation 4. Okay, so we deal with the non-Hermitian term. Okay, so eventually we'll rewrite the equation. We'll rewrite this equation. Let me rewrite it. Yeah. Okay, so the non-relativistic limits of Dirac equation becomes to the order of 1 over c squared. So this non-Hermitian term is cancelled, but you have a term here that you cannot neglect. That is this term. You have a new term here. This you must include. So you need to copy this and put it here. And then here, the wave function will become normalized here at the end here to show that it is a normalized wave function. Then you can kind of reorganize it better. Let me see. How can I make it look better? You can reorganize it. First, you group the rest mass. This is the biggest term. And then you have this this term. Okay, that's also to the leading order. I mean, yeah, the P here. The P is the leading order here. Okay, I mean this is the biggest order. Okay, because it's a very big number. This is the second one. You have a 1 over c here. Okay, so then you have this term. This is the non-relativistic limit. So this is the first term. So this is the relativistic correction. The relativistic correction of kinetic energy. Okay, so this is the first term. The second term plus dot E cross P. This is the second term. So the second term here, this is Zeeman effect. Zeeman effect. Zeeman term. And then this one is the spin orbit coupling. Okay, this is the spin orbit coupling. This is dot. Okay. Then you have another term. The electrostatic potential is here. You can put the electric field, the charge inside. Okay. And then this is the electrostatic potential. Electrostatic potential energy. And this is what people call the Darwin term. Okay. This is rest mass energy. Okay, and this is just a kinetic energy. Okay, the kinetic energy. Okay, so this is the Dirac equation in the non-relativistic limit to the order of 1 over c squared. I would say to me, This is one of the most important equations for electrons. Okay. It's important for condensed matter physics because in condensed matter physics, we don't usually deal with particles traveling very close to the speed of light. We deal with the electrons, and the fundamental equations for electrons is the Dirac equation. The Schrodinger equation is good to some extent, but it does not include the spin. It does not give us the spin-orbit coupling. Those are like important effects in condensed matter physics. Schrodinger equation is a bit too simple to deal with them. But you don't need a full Dirac equation because we don't need to deal with the positron. We don't need to deal with when the particle travels close to the speed of light. So we don't need a full Dirac equation, but Schrodinger equation is a bit too simple. So we need something more practical for us, and that is the equation that will give you like the knowledge that you need for condensed matter physics. So to me, I think this is one of the most important equations for me. And I like the fact that they can be derived in a very good way from the Dirac equation. So when you learn condensed matter physics in your courses, you probably learn them term by term. Like I remember in the book by David Griffith's textbook, they also give you a spin-orbit coupling, but they derive it from the picture, how the electron orbit this and this. I mean, those are also some kind of a pictorial way to derive the spin-orbit coupling, but it's not like I would say not as elegant as here from the Dirac equation and derive, and it's also not as strict. For example, the G factor of 2, if you just consider the Zeeman term by using just a normal, like a classical way of considering the magnetic moment, you'll miss a factor of 2. Okay, but here you have it here. Okay, so in condensed matter, when you deal with spin-orbit coupling, which is important, then that is the Hamiltonian. That is the Hamiltonian. You just use it directly. Okay, that is the Hamiltonian when the electrons travel in an electromagnetic field, and this is the Zeeman term. Okay, so let's talk about them more. Okay, so the rest mass is simple. Okay, this one you already learned this in the Schrodinger equation. Okay, so this is just the relativistic correction of the kinetic energy. Okay, so you have this in the dispersion of the energy. A Zeeman term, we talked about it in the last lecture, the G factor of 2. So this electrostatic potential, okay, it's straightforward. You learn it also in the Schrodinger equation. So the Schrodinger equation basically is this term with this term. These two are the Schrodinger equation. If you include this term, this is what people call the Pauli equation. Right? Schrodinger equation, and then you add 2 components, and then add the Pauli matrix, dot the B and take care of the G factor of 2. Then you get this Pauli equation. So the Dirac equation gives us 2 new things beside this correction, is this one and this one. Okay, that is what the Dirac equation gives us. So let's talk about the Darwin term first. So what is the Darwin term? You don't deal with it normally because this term usually give you very, I think it's small effect. Okay, so let's deal with the Darwin term. At least for me, I never need to consider Darwin term in condensed matter. So anyway, it is in the equation. So let's talk about it. What is the Darwin term? So the Darwin term is this. So you need to deal with this. Copy. So this is the electrostatic potential. So you know that when you have this operator on the potential, then it just gives you the charge. the charge. So is the contact interaction between the particle and the charge. What do you mean? Because this potential is generated by some charge. Okay, by some charge. Let's say the proton. The proton give you this potential, and then is the contact potential between the electron and the proton. Okay, they touch each other. That will give you some extra energy. Okay, they touch each other. This is the charge. This is the charge. Okay, so for example, for a Coulomb potential of point charge, let's say Z electron E, it becomes you include this as well. Okay, you include this. So after you include those constant term, the 4 pi here tensor partially the 8, then you have a Z E square, and then you have a delta function R. It will only affect the air states that does not vanish at the origin. Okay, so because you have the charge in the middle, and the Darwin term is a delta function of R. So only when your electron hit 0, then you have the Darwin term energy. So when you're in the S state, the probability at the origin is non-zero. So you will have the Darwin term energy. But when you're dealing with the P state, D state, all of those, the density at 0 is 0. So you won't hit this term. Okay. So the Darwin term is somewhat not important for all the other orbits, only for the S state. Okay. I mean, so far I have never read any condensed matter paper that needs to deal with the Darwin term. Okay. But it is there. It is there. Okay. So let's go to the important term of the spin-orbit coupling. This is the term that we need to deal with. Okay, let's deal with this thing all together. Okay, let's deal with this thing all together. Okay. So for this term, you can write it in this way. You can write it in this way. This is and then you are going to do it like this. Let me write in this way. We can forget about the wave function for now. We don't need the wave function. Just apply on it. Okay. And then you are going to let me see. So you can see that there's a this two. So let's make it multiply by 2 here. Like you over subtract it, and then you plus it here. Okay. Okay, you over subtract it. So why do we need it? We need to over subtract it because then you can sum them together. So you have a negative EH to MC, and then sigma, and then you can apply them like this, E cross P, and then you have an AMC here, and you have this sigma. Okay, so you can see that this term will give you something like the Zeeman effect, because this term is Zeeman effect, right? And then this part of the spin-orbit coupling will give you an effect like the Zeeman effect, and you only need to modify the magnetic field by this. Okay, so this is an effective magnetic field, effective B field, due to the motion of the electron, because you have a P here. P is the motion. Okay, so when the electric field is moving, it can experience something like there's a magnetic field. Okay, so we can actually see that this is just the Lorentz transformation of the electromagnetic field. So for example, in the left frame, that means you are the observer. You apply a E field. You apply electric field. This electric field does not need to come from the atom, just any electric field. So far, we have not said that we're dealing with atoms. We're just dealing with the electric field, with the electron in electromagnetic field. It's a very general. So let's say in the left field, you have some electric field. Then you have a electron traveling with the velocity v. It can be in any direction. Okay. Let me make it more general then. Just travel like with a certain angle. So the B field. Now here the B field is 0. Okay. The B field at the particle frame. At the particle frame is this equal to gamma. This perpendicular means it is perpendicular to, I think it's perpendicular to the velocity. Okay, to the velocity. You can see E cross V, right? Here you have a V here, the E here, then the cross will be in the outer plane, So you will experience a B field perpendicular to the motion and also perpendicular to the electric field. Is that okay? You have an E field like this, you travel like this, then you experience a B field like this. In the particles frame, because in the particles frame, it doesn't think it is moving, right? It is at rest. Then it will experience a different B field from the left frame. In the particles frame, the B field, the perpendicular component, is this. This is the perpendicular component of the left frame, and this is the modification. So this is the Lorentz transformation. Then of course you can write it as in terms of momentum. In terms of momentum, you just you just make it P. Make it P, and I just write it again. you have E cross P over MC. Okay, so this alpha is this factor. You learn this in relativity. It's approximately 1 in the non-relativistic limit. Okay. This is the Lorentz factor. Lorentz factor. Okay. So so you can see that this is what? This is just this term. Okay. So this is the left frame B field. This is the effective B field due to the motion of the particle. So you can see that in spin-orbit coupling, there is one part that is due to the effective B field due to the motion. And this part it will be relatively easy to understand if you know the relative effect of E field and B field. Okay. Okay, the second term. The second term is a bit tricky. The second term, this is what people call the Thomas precession. Thomas precession. So this one probably you don't know it. Okay. Have you learned the Thomas precession before? No? Okay, let's deal with it. Thomas precession. Okay. Okay, let's deal with Thomas precession. Okay, it's related to rotation. It's related to rotation. Okay, related to rotation. So let's consider. I mean, it doesn't need to be like a complete circle. Okay, so let's deal with a situation like this. Let's say you are taking a plane. Your plane is turning. Okay, it's turning. So in a simple case, let's consider a polygon like this. Okay. Okay, so let's say you're taking a plane. Okay, let's say you're taking a plane. Okay, like something like this. You're taking a plane. Okay, it travels at a certain speed, and then you're going to make a turn with the angle theta. Okay, you move it like this, then you make a turn. You make a turn with the angle theta. So let's say this length is L, and this length is W. So this is an n. This theta will be 2 pi over n. So n is the number of side. The n side polygon. Okay, you have an n side polygon. Let's say it's a regular one. Okay, so all the sides are the same. So this plane is going to move along this n side polygon. I mean, when you take n to be infinitely large, it becomes a circle. Okay, so when this plane is taking a turn, then you need to consider the relativistic effect. So tangent theta is equal to W over L, the width on the length. For the lab frame, okay, in the lab it's very easy. You just move like that. However, if you're inside the plane, you're going to see something different. Why? Because this length will be contracted. Okay, will be contracted when you're in the plane. The width won't, the perpendicular one won't, but the parallel length will be contracted when you're in the plane. You see a different width. So in the plane, you are going to see a different width, and the width will be different. So this width will be the same. Okay, only the length. So how much it will be contracted? It will be contracted by a factor of this. Now, so the Lorentz factor is bigger than 1, right? I mean, you subtract it, right? Bigger than 1. So length. So length is equal to this divided by the Lorentz factor. Okay. So it will be tangent theta. Okay. So that means you're going to see a bigger angle. This is very weird. They make a turn. In the left frame, you see that it is turned by a certain angle, but you're inside the frame, you will find yourself turning a bigger angle. So you have some extra rotation there. Okay, that is a relativistic effect. Okay, so for large n and small theta and theta prime, so tangent theta, when it is in a small angle, is just approximately theta, right? Tangent is just approximately. Okay, so you will have what? You will have tangent theta prime equal to tangent theta, then you just get theta prime equal to this. Okay, you just get it like that. So for one round, okay, so you get delta theta this equal to 2 pi so you see a difference in angle. The difference in angle is what? Is this minus 1 theta. Because this is slightly bigger than 1. So you rotate a little bit, then the change of angle will be slightly bigger. You have a difference in angle between the left frame and the particles frame. Okay, so for one round, so this will be, in one round you rotate for 2 pi, right? So you will have a 2 pi this. So that means the frame of the aircraft, of course, in the aircraft, is just basically the particle, has an additional rotation of delta theta. That means the particle the particle inside precesses for negative this in its frame. So because in the left frame it rotate like this, but in the particle frame, it has the extra rotation. Okay, extra rotation. Okay, so you should consider this. There's a particle inside the plane. The plane has an extra rotation. But for the particle itself, the particle never feel it is moving or rotating, right? In the particle's frame, it is always stationary. But the plane is turning, and turning faster than expected. So the particle will feel there's a precession that go to the negative angle. There's a precession go to the negative angle. Okay, you imagine there's a plane, the frame. You are in the frame. You are inside the plane. The plane is turning, and due to relativistic effect, in the plane's angle, there's a additional rotation. So that means the particle inside, it precesses for this in its frame. And so the precession slows down the rotation and reduces the energy, slows down the precession. So let me see how we're going to deal with it. So okay, let's consider the angular. This is a particle. Okay, the particle frequency and the outside frequency. Okay, so for every period, this is one period. The angle over the period. Sorry, P means doesn't mean particle. P means precession. Okay, omega P means a precession. So for every round, there's a precession. What do you mean precession? Precession means rotation of a rotation. Okay, when you're turning and then in the same time you rotate it, there's a rotation of a rotation. It's called precession. Okay, but of course the precession can be in the like you're rotating this way, the precession go the other way. I mean, normally if you have a rotation like this, if the whole thing turn like this is called normal precession, like those have a spinning top. Okay, it's spinning and then in the same time you also move it around. So this is called precession. Okay, for example, you have a spin like this. The spin means already rotating, right? And at the same time you also make it rotate like this. This is called precession. A rotation of a rotation is called precession. But of course, if you spin like this and you have a precession in the opposite direction, I mean, precession can be in the same or opposite direction of the original rotation, right? In this case, in this case, the precession is in opposite direction of the original rotation. Okay, of the original rotation. So this is called the Thomas precession. Thomas precession is you have a particle, you have a rotation, and then due to relativistic effect, there is a reduction. There's a reduction. So, for example, the precession every period, there's a negative omega delta theta on the rotation. And then the original frequency is 2 pi over t, right? So you make one round, you spend t. But every round, there's a precession in the opposite direction. So that is negative delta theta over t. So the t will cancel. And then this one is this. Copy. And then you have a 2 pi negative. So every time, so the frequency, the precession frequency will have a reduction of this one. Okay. So let's see. Okay, so that means omega p equal to negative theta 1. Wait. Oh yeah, omega p equal to negative omega 1 times this. Okay, so let's consider this. Let's consider this. Let's consider this is circle. Okay, so this is v. Okay, this is v, and then this is the acceleration, and then this is the phi. Okay, this is phi. Okay, so you have a particle moving in v, and then you have an acceleration in a. So what is the angular velocity? The angular velocity is omega times a sine theta. So basically, you take the perpendicular component. You take the perpendicular component. A. Then this is sine theta. I think I make a wrong symbol. Should this one should be fine. Sorry, some confusion in my note. Some confusion in my note. Okay, so basically a particle is moving, and then it rotates. Okay, so that rotation has an angular velocity. Okay, because every time you rotate, you need to take an acceleration, right? You need to take an acceleration. So this over the speed, that is the angular velocity. So a, this one, rotates with respect to this one. So this is the angular velocity. Okay. So basically, this is equal to this cross this v square. Okay. You just times v, and then this is just a cross product. A cross product. Okay, so this is the magnitude. The magnitude. Okay, so then let me put it here. So this will be We just consider the magnitude then, the magnitude. The magnitude here. Let me see, next. Sorry. And then V cross A, V squared. No, we don't need to consider this magnitude. So you can just cancel this. Okay, then let me see. You can take care of this factor. Eventually you get something like this. You can confirm this by yourself. Sorry, with the this. I'll leave it as an exercise for you then. Okay, so this one equal to this. You deal with the algebra. You can find it. Okay, so I won't bother to go to the details. So this one is approximately 2. It's approximately, is it 2? 1/2. 1/2. Because gamma is close to 1, right? Gamma is close to 1, almost 1, so it's 1/2. So it's about this. Okay, in the low speed limit. I mean, low speed means compared to light. Compared to light. Okay, the energy of a spinning object is 1/2. I is the moment of inertia. So I is the moment of inertia. Okay, so then the change of energy will be I omega, delta omega. You take the derivative, the 2 come down and cancel the 1/2. Okay, so what is this? This is just angular momentum. This is just angular momentum S. I mean, you can use this, and this is the precession. The precession. And I mean, of course, you can consider it. This will equal to the spin dot the precession. So that means a precession will contribute to energy. Okay, we contribute to energy, and it's very simple. Angular momentum dot the precession, then that give you the energy. And we have this. This is the precession. This is the precession. Let me see. This one, there should be a vector here. Okay, because here is a vector. Okay. Anyway, there's a vector here. So this will be 1/2C S dot A cross V. So basically put this term there, then you just deal with it. S equal to H_2 sigma, and P equal to MV, and what is Okay, then the force, okay, we use some classical. The force is driven by the electric field, and that equal to the mass times acceleration. It's just Newton's second law. So A equal to E cross M, and this V equal to momentum over M. So then delta E equal to this thing. Copy. Then you plug all of them in. You plug all of them in. You have H bar over 2 sigma dot E. This is acceleration. Okay, and then you have P. So eventually you get EH bar 4M square E cross P. And this is the Thomas precession term in the Dirac equation. Okay, so it is the energy that of a precession due to a relativistic effect. Okay. Historically, each of these terms, let's go back to this Dirac equation. I mean, the fact that I like Dirac equation very much is because it includes so many things in a simple equation. Okay, because the original Dirac equation is very simple, very, very simple. Okay, just alpha dot P plus the beta MC square. Very, very simple. Okay, but when you expand it, all these terms come out. Historically, people study these terms, I think, even before the time of Dirac equation, and they study them one by one, just from phenomenological discovery. For example, Schrodinger write down the Schrodinger equation, these two terms. Then people find the Zeeman effect. They know there's an internal degree of freedom of 2. So Pauli just has this Pauli equation. Okay, but that factor of 2, the G factor, he can never explain. Can never, because experimentally you measure the energy, you know that it meets a factor of 2. Then people just add there. Okay, they have different explanation and this and that, but this is just this is just one study for this term. And then for spin-orbit coupling, then you have the Thomas precession. Thomas precession, I don't think it was discovered by Dirac. Thomas, I mean, from the name you know, right? Thomas. So Thomas precession is a general phenomenon. You can even people can even see this effect in the planet motion, in the planet motion. As long as you rotate, then you have the Thomas precession. So it's not just for particle, even for astronomy, you have the Thomas precession. Then all of these different things that people study individually, you'll find that once you have the Dirac equation and make the expansion in the non-relativistic, then all these terms just come out. So when Dirac first wrote his equation, he expand them, then he find that all these terms come out. Then I think he's confident that his equation should be correct. And why so many people admire Dirac's equation is that the equation is so simple, so elegant, and all this complicated thing, each of these terms is kind of not easy to understand individually. But you find that it's so complicated, different phenomenon, and they all come together through the Dirac equation. And that's why when you have a lot of complicated stuff and you can kind of unify them into just one equation, and that is remarkable. And Dirac equation has such an effect. Usually when you study physics and you have so many different things, suddenly people tell you that they're just manifestation of just one thing. Then you just feel, wow, it's just very awesome. So Dirac equation give you like a very elegant description of different phenomena. Okay, we are running over time. So basically, we have this fundamental equation. So in the next lecture, I'm going to give you two examples of spin-orbit coupling that is related to our research, just from this part. So one is on the central symmetric potential in atom. So when you apply this term, you take the electric field to be the electric field of an atom, then you have the spin-orbit coupling that we usually deal with. And it turned out that it will depend a lot on the charge of the atom. When you have more charge, it will actually go I think it's to the power of 4. Spin-orbit coupling will increases quite dramatically with the charge. That's why in graphene it's quite weak. But once you go to MOS2, the spin-orbit coupling between much more significant. Okay, another example is called the rush bar spin-orbit coupling. That is when you travel in a 2D plane with a vertical electric field. That will give you a very interesting spin texture on the dispersion. We don't deal with rush bar dispersion in our research, but that is an interesting aspect of spin-orbit coupling. So in the next lecture, we'll deal with these two examples and from this term. Okay. So do you have any questions?
So for the Thomas precession, it's purely from relativity that we have this delta E, but then at some point we assume the gamma term is about equal to 1. I guess I'm confused by that.
This one?
Yeah. So in the low speed limit, I mean, why does it even exist? Because you should go to 0.
In the low speed limit, it is still there. It just you're taking the leading order term, because you already have a 1/c² here. It's just a matter of approximation. This term is there, but to the lowest order, to the 1/c. You don't have to take this limit. You can expand this to the power in terms of c. You find that the leading order is just 1. You can have more. But for us, somehow this 1/2, because eventually you are expanding this thing. The velocity is inside. You see, this velocity is inside is finite, and eventually you'll find that you're basically expanding this velocity somehow. You get the c here. And I mean, it's not very straightforward. If you want to know it, you can just do this calculation by yourself, because there's a velocity inside gamma, and there's a velocity outside. When you combine them together, you'll find that you eventually you get this term to the leading order. Sorry, it's not just that. You also have a velocity here. You have a velocity here. You have a velocity here. So eventually, you'll find that what matters is just this velocity over c². So the velocity still matters. But to the leading order, to the 1/c² order, that is the term that we consider. So basically, this is an equation that is only good when your speed is not very close to the speed of light. Once you travel close to the speed of light, then this equation is no longer good. And then of course, in that case, you have to consider the full 4-component Dirac equation. Like the positron part becomes important. So this is no, but for condensed matter, we never need to consider that case. So for Dirac equation, this 2-component equation is all you need. And I have never seen a case that you need to consider a higher order term, like a 1/c to the power 3 cases. Like I have never seen. So this is, I would say, just for condensed matter. For electron, this is all you need for condensed matter. So I mean, if you discover effect that is beyond this equation, then you can work on it and write a paper. But so far, this is what we need. And among this term, the Darwin term looks like is not that important. the most interesting thing basically comes from this one. And among them, this is still relatively simple Zeeman effect. And a lot of the interesting thing basically comes from the spin-orbit coupling. That is the part that give you interesting physics in condensed matter. And the spin-orbit coupling can be, usually that is the part that affects the spin. If you're dealing with spintronics, like anything related to spin of an electron, that is the Hamiltonian that you're looking for. You can see that among all these terms, only 2 terms include the spin, this one and this one. And this is a relatively simple one Zeeman term. So basically, if you want to study any spin phenomena related to electron, and then you know that for one electron, the Hamiltonian is this part. Of course, when you have a lot of electrons and you combine together, you have more complicated phenomena. But just one electron, how their motion affects their spin comes from this term. Okay, and this term is for B field. This term is for electric field. Okay. Okay. Any other questions? For Thomas precession, I confess that even I myself don't quite understand it. Like it's I mean, mathematically, I can write all these steps and prove it, but it just like pictorially, I just feel difficult to imagine it. Like the relativity effect is like that. Like, when you have a relativistic effect and combined with the rotation, you just have difficulty how to visualize it. So it's understandable that you feel so confused about it, because I myself also don't feel very clear that I understand Thomas precession. I mean, if you can visualize something, you feel you understand. But for Thomas precession, I still feel it is kind of difficult to imagine. Like how in one frame and the other frame you rotate in a different frequency. But you can maybe go through the steps and try to imagine, like try to visualize it to convince yourself that it is there. Okay. Okay, any other questions? Okay, if no more questions, then we'll stop the lecture here. Thank you very much.